Test, test, test. Can you guys hear me for those joining on the Zoom? All right, thank you. All right, good evening. Let's get started. Let's finish the surface integral today, but as a quick review, okay, this is directly taken out of the formula sheet. Okay, so this is the formula sheet you have, okay, and on top of this second page, this is the formula for surface integrals. So what we have done are the three special ones. When you have a spherical surface centered around the origin, when you have a cylindrical surface centered around the z-axis, and when you have a plane that's parallel to a certain special, right, either xy plane or yz plane or xz plane. Okay. Today, let's look at the last one, more of a generic type of surface. Okay. So if a surface is expressed as z equal to f of xy, for that, oh, you cannot see the screen, right? Share the screen yet. Let's see, where is the sharing here? Can you see my screen? Okay, so I cannot see on my computer here. Okay, good. So today we're going to learn the last type of surface, the generic surface, and the surface is z equal to f of xy. So we call this is case number 4. When you have a surface expressed as z equal to f of xy. And if you recall that, we call this kind of thing as explicit surface, because this is an expression explicitly describing this z component. Right? So we did this quite a lot. We have a paraboloid, we have a plane, right? They all fall into this category. As long as you can express your surface as z equal to a function of xy, then this is the case number 4 we're talking about here. Okay? A generic surface can be sketched like that. Of course, if you have the expression, you can sketch it very precisely. Surface integral formula is about, this is a generic surface integral formula. And we call this the flux. Okay, so surface integral as flux. Now, technically, there's also surface integral of a scalar surface here. So this is vectors, but anyway, so we're talking about flux concept, or in other words, is how much of this vector field F, okay, will go through this surface. Okay. Could be either way, every surface has 2 directions. Okay. And then that's give you the totals, the results of the surface integral, you give you the flux. Okay. Now, what the typical approach for the other 3 surfaces, as you can see here, is you need to identify what n hat is. Okay, so plane, spherical, cylinder, and you identify n hat, n hat, n hat. And also we need to identify the dA. Okay, so dA for plane is this, for spherical is this, as for cylindrical is. So all of the dAs are being expressed as 2 variables within that either cylindrical coordinates or spherical coordinates or the Cartesian coordinates. Okay, so all the other 3, the approach is to find the n hat, find the dA, and then substitute into this formula, and you calculate the double integral at the end. Okay. Now, the case 4 is a slightly different. Okay, the case 4, I'm going to present you with the final result first, and then I'll go try to go through this a little bit to just roughly see how you get it. Okay, so for case 4, instead of finding n hat dA separately, so we actually can find the n hat dA in one shot. Okay. So the results for n hat dA is this. So positive and negative fx, negative fy, and 1 dx dy, or dy dx. It doesn't matter. So what I'm giving you here is a result. Okay, so then I'll talk a little bit how this result is obtained. So you can clearly see, also in the formula, you were not given specifically what n hat is or what dA is, but I'll give you actually specific what n hat dA. But all you need to know is what's n hat dA, okay? And then you'll be able to calculate this surface integral. But this is the result, okay, for n hat dA. Okay? So let me write down a few steps first based on this result, and then we can roughly go back and to find how n hat dA is derived. Okay. All right, suppose that you already, you have the formula, you have the n hat dA out of here. Apparently this is a vector, right? Because n hat is a vector, dA is a scalar, so together you still get a vector. And there are two directions, positive and negative, which makes sense because for every surface, there are always two orientations, right? So how we're gonna go from here then, right? So you got n hat dA, and you have your surface integral over here. So let's see what happens next with this n hat dA. Of course, we're going to substitute this n hat dA into this surface integral formula. F is a vector field. So let's say we have used M and P representing this vector field. So 3 components. Each component is a vector, is a function of x, y, z. If you have the vector field given, right, then you know what the M and P's are. So M and P, okay, substitute for the actual vector field, then dot, positive, negative, the n hat, this vector at here. So negative fx, negative fy, 1 dx dy. Okay. I probably should clarify this. Fx is partial f, partial x, and this is partial f, partial y. If you recall the notation y. So this is your surface. So what happens here, you need to calculate 2 partial derivatives based on the given surface. Partial f, partial x, partial f, partial y. Okay. Right? So now I have the next step. I need to do the dot product. Okay. So the dot product give us, let's take the positive and negative outside. Of course, for an actual question, you will pick a sign, right? Either positive or negative. So you're not going to keep both. Dot product, m multiply negative fx, and then n multiply negative fy, and then p multiplied by 1 dx dy. Okay. So this is the initial results after dot product. Now after dot product, so you look at the double integral right here. It's about the x and the y. Okay. So it's about x, y, so there's no z, right? Because it's double integral. You don't need 3 variables to calculate a double integral, a surface integral. So you only need 2, in this case, dx, dy. So there are 2 things you need to be clear. First of all, the x and y limits, okay, the x, y limits, which is what you need for calculating the subsequent double integral. And they are determined by, okay, they're determined by the shadow. Okay, shadow of the surface in XY plane. Okay, yeah. So that XY, how you find the limits. Okay, if this is a surface S, then you drop it, okay, into you drop it into the XY plane, however it looks like, okay? That region R will give you the limits for X and Y. Essentially the same procedure as you go through a double integral when you integrate over region R, right? A Cartesian, you pick an order and you draw arrow lines in the axis direction first, find the first contact, second contact, and sweep to find the first edge, second edge, right? So all of these double integral typical procedures. Okay? So your X and Y limits are determined by the shadow of the surface in the XY plane. And second comment is that, okay, if you look at this double integral here, it's all about X, Y, there's no Z. However, if you think a little bit deeper here, okay, for the MMP function, okay, the vector field, their nature is a function X, Y, Z. Okay, so for example, maybe you have a Z here, you have XZ, XY here, maybe you have a YZ function, for example, right? Yeah. So if I plug in this MMP over here, here, then guess what? You will have a Z variable showing up in this bracket. Okay, but then you don't have dz at here. So what are you going to do with a Z? You cannot keep the Z there, right? Otherwise, you won't get a. If you keep a Z over there, then you won't get a results out of this double integral. So you have to get rid of that Z. So how do I get rid of the Z? Surface. And you're integrating over the surface. And that's what Z is. Okay? The Z is equal to f of xy. So when you're dealing with the result of the dot product at here, you need to substitute the Z with Z equal to f of xy. That's an expression for the surface that you're dealing with at here. And that's a surface you're calculating the flux out of it, okay, either this way or the other way. So these two are the key points to make sure that you can actually obtain a result of this surface integral. Okay. So I should probably write the second one first. First, you have to substitute the Z with Z equal to f of xy, and then you find the limits, and then you carry out the double integral. Okay. So we'll take a look at the examples next, but let me get back to this formula for the n hat dA. Okay, so to roughly illustrate how n hat dA is obtained, okay, without going too much into the details. Okay. So how n hat dA is actually equal to positive, negative fx, negative y, and 1, and dx, dy. So I'm going to borrow a diagram from my lecture notes at here. So this is more or less basically a proof, how this is derived here. So you have detailed proof in the lecture notes. So the general idea is you have a surface over here, and you create a very small patch on the surface. How the small patch is created is this. So first, pick a point xy in the xy plane, and make sure that xy is part of the shadow of the surface, right? And then you change this xy by delta x, delta y in either directions along the x and y axis. So you create a rectangle right here, with each side of the delta x, delta y distance. Okay. Then after you move delta x in this way, that's the coordinate for this corner. After you move delta y in the y-x direction, and that is the coordinates for that corner. Then this little patch in the xy plane, if you extend up to the surface, then you get, similarly, you get a little patch, okay, on the surface. So this little patch is what we call delta A, right? If it's small enough, it becomes a dA. Okay, so dA is basically that dA over there. Okay. And second of all, if you recall that for any small patch, okay, on the surface, you always have basically a perpendicular vector, right? Normal to that little patch or normal to the surface at that location. Okay, so that's what n hat, right? N hat is a normal vector to the surface at a certain location. Okay. And we're looking for n hat dA, right? And if you go through this lecture, you'll see that this little patch, which is created based on the shadow at here, and you can create two vectors, u vector and a v vector, okay, representing two sides of this parallelogram. So this is u and a v representing a two vector representing two sides of parallelogram. As we learned from the first lecture, right, or second lecture, when you use u cross v, right, you have a parallelogram, you have two vectors representing the two sides of the parallelogram. And when you use u cross v and then take absolute value of that, I wonder if you remember what you get. Sorry, what do you get? Yes. No, I use a absolute, yes, very close. When you use this, you actually get, you get the magnitude, but this magnitude represents, yes, limit. Length, not the length of projection. So area, exactly, right? You get the area of the parallelogram. And that's basically dA we're looking for here, okay? And at the same time, if I just look at the cross product itself, and cross product is what? You know, when you cross product this way here, you get a vector, and that vector is naturally a vector perpendicular to both u and v, and that's basically what we're looking for, right? We're looking for a vector n hat perpendicular to that location. So this u hat cross v has two informations, exactly what we need. We need a vector perpendicular to the location. We need a magnitude of for the small area delta A, which are all given by u hat cross v. So if you calculate this one here, that end up actually just n hat dA. So that's basically what the proof, the procedure of the proof, I will give it to you. Okay? So if you're interested, you can certainly look at the detailed proof in the next page, and you'll find it, you know, the cross product itself give you this n hat dA. Okay, yeah. So that's how n hat dA is derived, right? For the exams or solving questions, my expectation is that either you memorize n hat dA or either you know where to find n hat dA using formula sheets. Okay, so that's expectations for n hat dA, not for n hat, not for dA, but for n hat dA together. Is that clear? Yeah. However, I do want to give you what n hat is, what dA is separately, okay, just for your curiosity. So and then what is n hat? And what would be the dA? If I find n hat, then actually I will be able to find a dA, right? Because I already got n hat dA. Okay. So let's see, what would be the n hat then, right? N hat, as a matter of fact, you can obtain it based on what we have learned. So first of all, here is a surface, okay? Now z equal to f of xy. Okay. So if you can recall using the knowledge we have learned, okay, I'm asking you at this point of the surface, can you find a vector, okay, not unit vector, just a vector first. Can you find a vector that is perpendicular to this surface? What will be a candidate vector that's perpendicular to this surface? Yes. Nope. Not that complicated. Actually, just one single word. Yes. Normal vector, yes, that's what I'm looking for. But what is a candidate for this normal vector? You have the surface here. No, not key hat, not necessarily always key hat, right? It's a generic vector. So how about this? Remember, right? If I create a lot of level curves, what is a vector perpendicular to the level curve?
Gradient.
Sorry, Connie. Not a tangent, right? So here's the surface. Here is a level curve for this surface. If I ask you, what would be a vector perpendicular to the level curve? Actually, part of the assignments. Yes. Pardon me, louder? Not key hat. Here's the surface. Here's the level curve of the surface. Dylan. Grading vector. Okay. So grading vector is perpendicular to the level curves. But now I'm asking different, right? I'm asking is, what will be a vector not perpendicular to the level curve, perpendicular to this surface? Yes. You don't need a parametric equation, right? Along the same line, so you calculate the gradient of this f, you'll get a vector perpendicular to the level curve. So what would you do to get a vector that's perpendicular to the surface? Along same line here. It's still gradient, but this time it's a different gradient. Gradient of what? This is a gradient of the function f, right? So you need to also calculate gradient, but this time what gradient you need to calculate? The level surfaces, exactly, right? You need to calculate the level surfaces. What is the level? This is the level surface. So usually, if you recall that, right, what we do is we create a new function. We call it the z minus f of xy. So when w equal to 0, you get back to this surface. This is a level surface. Then del w, if you calculate the del w, that will be perpendicular to this z equal to fxy. Right? Grading vector is the nature of the grading vector is depending on how you interpret it. If you have a 2D grading vector, it must be perpendicular to the level curve. If you have a 3D grading vector, then it must be perpendicular to the level surface. So all you need to do is to calculate del w. That will give you the candidate of this n at here. But I'm looking for is n hat, right? So then normalize it, you get the n hat. Then what is del w? So this is your del w here. Okay, del w basically give you, so if you calculate the partial w, partial x, partial w, partial y, partial w, partial z, so you get exactly this negative fx, negative fy, 1. This is the gradient to the level surface, to this or to this surface at here. The reason we call it level surface is basically, right, this is just a surface, level surface for this w function when w equal to 0. And this is your candidate n here. Then you normalize the n, you get your n hat. You get your n hat. Yes, that's your n hat. And also remember what n hat dA is. This is n hat dA, right? So we have n hat dA. Let's rewrite it over here. Let's just write a dA here. Is that good, right? I think irrespective to whatever we're learning here, the grading concept, right, it is a standalone concept. You know, you have a surface and you want normal vector to the surface, then the normal vector, unit normal vector is calculated this way here. Okay. So you got your n hat. and you got your n hat dA. Then when you look combining these two equations together, and you can solve for dA, right? dA, remember what dA is? dA represents a very small differential area on the surface S. Okay, so dA you combine together, what do you think would be dA? Because you already got a negative fx, negative fy1 over there, and then n hat is this term. So dA, you got to cancel this denominator here, right? So dA must be fx squared, fy squared plus 1, and then dx dy. That make sense? Yeah. So this dA, okay, this is a, let me just write down a little bit more. This is called a differential area on the surface S, okay, on surface S. Okay. So if you have a surface, okay, and you create a very small patch over here, dA, okay, so that's what dA is. Okay, you can calculate this, and the S is represented by Fz equal to f of xy. Okay. Now, whatever I'm doing here is a little bit above and beyond, so it's not going to be tested in the final. Okay, but as I said, I've repeated. My expectation is this is the formula you need to remember. Okay, for surface integral. Of course, if you can remember the two formulas over here, you get exactly the same formula, right, as a surface one. Right. So now, what's so good about this one here? Okay. Think about the next time, if you have an application, say, can you calculate the total area of this surface given by z equal to f of xy? Okay, so you have a certain kind of a surface hanging in a 3D space. Then how do you calculate the total area of this surface, right? So you have this S over here. If you want the area of this surface, and guess what? All you need to do is you integrate like this, right? Just integrate dA, and you get the total area of the surface. You know, very much like you integrate a volume of a region, you get the volume, right? Application. So if you have such kind of question, all you need to do is substitute dA over here, and then calculate the rest of the integral as if it's double integral. And that's basically how you can make use of the dA right here. And one more application is, suppose that you have a density associated with this surface. Okay, so you pick a point on surface, it has a density delta. Then what will be the mass of this surface? So the mass will be density times dA, right? So density times dA give you a small mass, and you integrate over, you add over all the whole surface, then you get a total mass. Right? That's another application of this. As a matter of fact, this is called a scalar. This format of surface integral is called a scalar surface integral. In contrast to what we are doing, calculating flux, is called a vector surface integral. What does that remind you? We have a scalar line integral and vector line integral, right? Yeah. Okay, so that's surface integral, okay, in terms of x-split surface. Let's look at an example how we can actually make use of the formula. Giving a vector field F equal to Z k hat, and also a surface that's what's going to happen next. And also a surface Z equal to x squared plus y squared. and z is between 0 and 1. So once you have this surface, you should be able to sketch. It's a paraboloid because z is between 0 and 1. So the top surface is at 1. And the side is z equal to x squared plus y squared. And we need to calculate, okay, so calculate what is upward flux. What is upward flux through this surface S? Okay. So upward means, that's a direction, right? The direction going up. So the first question is, okay, let's write down the surface integral formula here. Okay. And of course, we know n hat dA. Okay, let's put down n hat dA first. Okay, the original formula n hat dA is positive, negative of this vector times dA. Okay, so the next question is, should I pick the positive or should I pick the negative? Right, and that's basically a decision you have to make. Now you look at the question here is asking for the total upward flux or flux in the upward direction. Now what is upward, right? Upward and technically is in the direction of the z-axis. Okay, so your choice of n hat dA or the positive and negative sign. Okay, you look at this formula right here. Okay, so you have two different vector. One vector is this, and the other vector is this. Okay, so basically, which vector will actually give you an upward information is your choice for this particular question. You know what I'm saying, right? So if you compare these two vectors, okay, now this is how you interpret it, and later you don't need to actually interpret anymore, just have to remember this. So let's say, for example, right, if I look at this vector, the first vector, so you got a something, something, 1. And whatever these first two elements are, when you have a last element as a 1, then guess what? Let's see, for example, right, you can try it. If you have a something 1, basically the last z component is a positive number, then that particular vector definitely will pointing, even not if it's strictly pointing upward to the z-axis direction, but that vector will has a component that pointing to the positive z-axis direction. Right, so that 1 there will determine the vector like pointing either this way or this way. Definitely not going to be this way. And this one here is actually because of the second one, you put a negative in front of the 1, you guaranteed this 3D vector will actually have a negative z component. So the positive sign at here refer to upward flux, and the negative sign at here refer to a downward flux. Okay, yeah. So let me see, this is called basically upward, and this is downward. Okay. That's how you determine how to pick this negative or positive based on the question. Now, don't confuse with an enclosed surface, all right? Yeah. So when you have an enclosed surface, you have to tell things differently. For example, in this question, we're only referring to this parabola surface. Now, if a question say a surface consists of this top z equal to 1 and plus the bottom surface paraboloid, then you're actually dealing with two surfaces, right? So in that case, we usually don't see upward, we'll see either outward or inward. Does that make sense? Yeah. You only see upward or downward when it's open surface, basically. Right. So that's why we're going to pick this positive sign here for the calculation of this question. So let's take a look at the calculation. Okay. All right. So n hat dA, okay, equal to this negative fx, negative fy, 1 dx dy. I got my surface at here, which is x squared plus y squared. So that's your function f. So the partial derivative got 2x, negative 2y, and 1 dx dy. Then the surface integral is f dot n hat dA. F is given as z hat, which is 0, 0, z, dot the n hat dA, dx dy. Okay. Altogether, you get 0, 0, cancel the first two terms, you get just a z and dx dy over the acid here. So this is a perfect example. You know, you got a mixture of x, y, and z. You have to get rid of the z. So what do? You replace the z, right, with the actual surface, which is x squared plus y squared. Okay. And the xy limits needs to be determined by the shadow of the surface in the xy plane. So the shadow of the surface, if you look at this question here, essentially it's a circle. Right? When you project the shadow into the surface, it's a shadow x squared plus y squared equal to 1. So your double integral at here, I mean, you could literally replace this with r as representing the shadow. Okay. And then from here, you proceed to do a double integral. So you got Cartesian coordinates, you got polar coordinates, and because the current shadow is the circle, so you should probably consider polar coordinates, right? So if you consider polar coordinates, then you substitute x with r cosine theta and substitute the y with r sine theta, right? So r cosine theta, y equal to r sine theta, okay, is the polar coordinates. Substitute into this x squared plus y squared, you get r squared. And the polar coordinates, you get r dr d theta. To determine r limits and theta limits, right? So r is 0 to 1, theta goes 0 to 2 pi as usual, okay, for polar coordinates, and you calculate the rest of this integrals should be fairly straightforward. So you get pi over 2. Okay. So as you can clearly see, you know, once you set things up correctly, the rest of the step here is nothing new, right? It's just basically a repeat of what you have done for a double integral. Good. Yeah. So the key thing is identify the wording. Is it upward, downward? Identify the n hat dA properly, and then substitute everything, determine your best action, Cartesian or polar, determine the limits, and calculate this integral. Okay? Yeah. Now, if you're interested for surface integral, I do have one more case, which is using parametric equation for a surface. And there's another one actually, implicit surface. Okay, so look at the lecture notes if you wanted to study a little more about the surface integral. Okay. Any questions? Good. All right. So let's continue. Basically, that will lead us to pretty much the last topic, okay, last couple topics of this class. Okay. Essentially, there are two theorems we need to introduce. One is called divergence theorem. The other is called Stokes theorem. Okay. Before we introduce this divergence theorem, let's introduce the last operator. Okay, and an operator called divergence. Not the movie Divergent, it's Divergence, right? You know, if you recall so far, what operator have we learned? Right? We learned a couple of important operators, partial derivative operator, right? And we learned gradient operator, and we learned del cross operator. What's del cross operator called? When you del cross F, what is it called? Curl, right? So you can always repeat in your head, gradients give you a vector pointing to the direction that is greatest increase in the function F. And the curl operates on a vector field. So curl, if you recall, give you what information? What does curl? Yes. Excellent. Microscopic rotational information of the vector field, right? So if there are three things that you need to remember out of the course, 1, 2, and the third one, it'll be the divergence. Okay, so what are the meanings of these things? So divergence, let's start with definition of divergence, okay? So definition of divergence. Divergence also operates on a vector field. So actually divergence of a vector field. Here's the definition. We write divergence as divf or del dot f. Okay, both ways are fine. Just like a curl can be written as a curl f or del cross f. Okay, so these two the same. So divf or del dot f is defined as limit. The numerator here is a surface integral. And denominator is dv, the del v, like this. Okay, so that's the formal definition of divergence. So let's study this limit a little bit, okay, and understand the meaning of it. Okay. So first of all, let's take a look at the numerator. Right? The numerator is a surface integral over a closed surface S. So if I draw an arbitrary closed surface S, okay, so let's say this is S enclosing, it's because it's closed, then it must enclose certain volume, right? So the volume at here enclosed by the S is given by this delta V. So delta V at here is the volume, okay, enclosed by this S, surface S. Okay. And then the limit, okay, I didn't finish quite the limit. The limit is to let the delta V go to 0. Okay, so now I think we're ready to interpret it. Number one, the numerator. So either way, dA vector or impact dA. The numerator here, that's basically what kind of calculations? To give you what? Surface integral give you the flux, right? Give you the total flux. Okay, let's see, out of S. It's the total flux out of the F at here. It's a surface integral flux or net flux. Okay. And then you're using a total flux out of S or net flux over S. So basically, the limit here, you have a net flux over a certain small volume. So let's call it unit volume. Okay, it's called a unit volume here. Okay. And basically, this is the definition of divergence. Okay. Definition of divergence. And better yet, let's see if I'm asking you, you have a mass over a volume delta V, and you let the delta V go to 0. So what quantity should you get? If you use the similar concept, you say, okay, I'm calculating a small mass at this location and divided by the volume, okay, delta V, but I'll let the delta V go to 0. Yes, let the limit, take a limit to let the delta V go to 0. So you will get mass density, right? So right now, what you're doing here is you're calculating a total flux out of the surface S, and then divided by delta V, and let the delta V go to 0. So if I use exactly the same analogy for mass density, what should I get here? So if a mass is on the numerator, you get a mass density, and now you got a flux on the numerator. You should get what name? Flux density. Right. So this integral, this limit here, basically give you a flux density. So what does mass density mean? The mass density means how concentrated at a certain location of this object. And that's what density basically means. If I have a flux density, then technically I should get information is how intense this flux flow, right? At that location. That's density concept. Okay. So couple comments. Flux density, which is essentially divergence, or del dot F. Okay. It's a first of all, okay, this is a point concept. A point concept means you plug in certain coordinates x, y, z into this, you get a value. Dot product give you a scalar value, right? You get a certain value, maybe 2, maybe 3, maybe -2, maybe -3. Right? You get a certain scalar value. Okay, that's why I call it a point concept. Gives a scalar value. Okay, so it could be more than 0 or less than 0, or even equal to 0. Okay, so this flux density calculation or divergence calculation can give you either the 3 values at here. Okay, that's first observation. That's a very direct observation. And second observation, because you're talking about it's a flux density, and the scalar value that you obtained here will describe essentially is a flux actually getting out of this point or actually going into this point, or there's nothing going in and out of this point, and that's 0. Right? So that's this information in here essentially will tell you, so del dot F, it gives the amount of flux, okay, either entering or leaving a point. This is actually a very neat calculation. You have a vector field, okay? Imagining the vector field as a sort of certain flow of air or flow of a river. And you might be interested at a certain point within this vector field. Is there something actually going into the point, or is there something getting out of the point? Right? That's given by del dot F. So we usually call, right, if del dot F is more than 0, if this divergence is more than 0, we call it, so more than 0 means what? You have something getting out of this point. It's like something overflowing out of this point. It's like a faucet. Once you turn it on, water is coming out of it, right? So we call this is a source. We call the point as a source. And if this is less than 0, then just like the courtyard, the water fountain, right in the middle of the water fountain, what do you have? You have a sinkhole, right? So water is going into that point. Okay. And of course, if it's equal to 0, then there is nothing going in and out, or out of this particular location, right? So if this equal to 0, it's called a balanced point. Okay. It's balanced out. Right? So that the divergence now essentially, if you going back to the three things: gradient, curl, divergence. So they give you three different, very distinct physical interpretations, okay, within an actual vector field or within the actual 3D space. Okay. So there's a diagram I can show you here. This diagram. So yeah, so this diagram here. So let's say you have an object which is with certain area, you place that within vector field. If it is very evenly distributed vector field, then you can confidently say that del dot V actually equal to 0. But in this case here, they're more getting into it than more out of it. So then it's functioning as a sink. This one, they're more getting out of it and it's functioning as a source. Right? That's basically what it is. Right? Now, other things is that I want you to prove a few things. Okay. So first of all, del, you can show that, okay, del cross, we can show, okay, we can show this. If you calculate del cross del F, okay, if you calculate del cross del F, so first of all, what's del F? Give you a grading vector, right? So if you calculate the curl of the grading vector, and you can easily prove it's 0. Okay? So if you calculate the curl of the grading vector, you get 0. And if you calculate the divergence of a curl, so if you calculate divergence of a curl, so del cross F give you a curl. Right? It's a vector field consisting of this curl. It's also 0. Okay, there's two interesting findings that are here. There's actually better explanations, but we don't, because of time, we don't have this. But the curl of the gradient equal to 0. Okay, it's something that you probably can easily memorize using this cartoon right here. Okay, so the gradient is asking here is, who wants to be on my team? Did you get it? Because gradient cannot curl, right? So that's how you can memorize this formula here, right? Yeah. So these two, if I got time, I can interpret this a little bit more here. But anyway, we're kind of running out of time in here. So in the next lecture, we'll look at how we can make use of a divergence and apply to a divergence theorem and the Stokes theorem. So we should be able to finish within one lecture. Okay, we'll see you next Monday.